on graphing rational functions. And we're going to need to do three things. We're going to need to write the equations of the asymptotes and label them on the coordinate plane. We're going to need to enter at least 5 values in the table of values, and we're going to need to graph the function on the coordinate plane. Okay. Actually, let me get the handy dandy pen here. And okay, so here is the function h of x equals 9 divided by x over 1 plus 3. Here's a table of values that'll be given. Basically, you know, here are all the x values, and then h of x, or another way to represent h of x is to think about it as y, right? We're not going to take a look at this. We'll take a look at this later, but let's first look at writing the equations of the asymptotes and label them on the coordinate plane. Before we do that, I want to do a little bit of review about asymptotes. And so let's just take a look at the rational function graph family, and so you can get a basic understanding of how these behave, what the graphs look like. And so here's what's considered the parent function. It's f of x equals 1 over x, and this is what it looks like, right? As x increases, it gets closer and closer and closer to the x-axis. As the values of x get higher and higher, the function gets closer and closer to x, right? And actually, let's do a little naming here. This curved line is called a branch, okay? And likewise, this is a branch, so there are 2 branches. And as we see, as the values of x get closer and closer to 0, the function, or the branch, gets closer and closer to the y-axis. It never touches. This picture is a little misleading because it actually shows the branch touching the y-axis, but it never touches. Likewise, it never touches the x-axis here, and for negative values of x, it never touches the x-axis or the y-axis. It gets really, really close, but never touches. It's more like you see here, with a little bit of space, a little bit of a gap between it, but it'll be imperceptibly small as you go down towards infinity. So one of the important things that we're going to need to be able to do is identify, because we're given the general form of the function f of x equals a divided by x minus h plus k. We're given that general form, and you're going to have to be able to label and pick out what is a equal to, what is h equal to, and what is k equal to. So let's try to do that real quick for the parent function equals 1 over x. And we know that we're looking at the general form of a over x minus h plus k. And you say to yourself, okay, well, we need to find what h is and k and a. Well, what is that? Well, we don't know. But you know what? We can write this parent function in a form that will mimic the general form. And how do we do that? Well, watch. It's just 1 over x. Well, is there an h here? No, there is no h here. Well, what can we do to hold the place of h? Well, I guess 0 works, right? We can use 0 because x minus 0 is just still x. It doesn't change. It doesn't change anything. Well, likewise, we've got a plus k. I don't see a k here, but can we put something in its place to hold its place? Well, yeah, of course, 0, because we can add anything to 0, and it doesn't change its value. So now we can look at the parent function and clearly understand and or identify, be able to label what a is. A is equal to 1, right? It's just what's in the numerator. H is equal to 0, and k is equal to 0. So that's the parent function, and that's being able to pick out and or label the various pieces a, h, and k from the parent function. Okay, let's take a look and see how the parent function changes when we change the values of h and when we change the values of k. Okay, the blue part of this graph here is g of x equals 1 divided by x plus 5. It's plus 5. So we don't have an h, but we have a k. We have a k of plus 5. And look what it does. It takes kind of like the x-axis and pushes it up here, and we get this line y equals 5. And that's the line at which the branch will come close to but never touch. On the it's a horizontal line, and this is called a horizontal asymptote. Okay, because you can see the branch is coming down. As x increases, as x gets larger and larger and larger, it gets closer and closer and closer to the line y equals x, but it never touches it. Again, this is not an exact representation, because if it was, the branch would be, there would be space between the dotted line y equals 5 and the branch, but that's not there. But what it does is it illustrates what happens when k changes. When k is 5, it pushes it up. Likewise, if a k were -5, it would push it down the y-axis, and the horizontal asymptote would be y equals -5. It'll be right about there, okay? And now let's take a look at what happens when we change when we change h, okay? H becomes 4. Well, here's the function. H of x equals 1 over x minus 4. And what it does is it pushes the vertical asymptote to the right 4 places. And it becomes the line x equals 4. And so we'll see. So we see the red function as it gets close to 4. It never, as the value of x gets close to 4, it gets closer and closer and closer to the line x equals 4, but it never touches it. Likewise, from the left-hand side, as it gets closer and closer to 4, it never touches it. And look, we can make sense of this, because remember our friends domain and range? Domain and range, sorry about the sloppy handwriting, gosh. Well, domain are basically the inputs. And if we take a look at this function here, we know that x can never equal 4. X cannot equal 4, because what happens when x equals 4? Then we've got 1 over 4 minus 4, and that's 1 over 0. And that is undefined. Defined, right? It's undefined because we're saying the same thing as 1 divided by 0, right? 1 over 0 is equal to 1 divided by 0. And if we could do it this way, 1 divided by 0, we could say, okay, what can we multiply? We put something in this box. Can we put something in this box to multiply by 0 to equal 1? Nope, you can't find anything, so it's undefined. And so it's real clear the vertical asymptote is the line that is equal to when the domain is undefined. Let's take a look at what happens when A changes. Okay, so when A is, we've got a couple different things that I can do. A can be negative, or it can increase or decrease in size. So when A is negative, what happens is it reflects across the x-axis. So here we have this blue branch right here, which represents, well, here's the red branch represents 1 over x, the parent function. The blue branch here represents the function g of x equals -1 over 2x, and what happens is it reflects over the x-axis. But not only that, but a here in this one is a is equal to -1/2. So a is getting smaller, and as a gets smaller, the curve, or right here, it gets closer to origin. See how in the parent function, the right at the center of the branch right there, it's kind of further away from origin, and it gets closer. Likewise, if we were to have a equal to, say, 10, then it would be kind of even further still. It would be like this. It would be further. It would get further away from origin. Okay. So here we have our function h of x equals 9 divided by x plus 1 all plus 3. We need to identify h and k, because that gives us our vertical and our horizontal asymptotes. So how can we do that? Well, we need to make our function mimic or look like the general form. And the general form we could see is a over x minus h. We have a minus sign here, but we have a positive sign in our function, so we're going to need to change that. We're going to need to do something there. And it's plus 3, but there's a plus sign here, so we should be fine right there. So let's say h of x equals 9 over x. We need a minus sign there. Minus, well, what do we have to do with that? Make it a -1 plus 3. Because watch, right? A negative times a negative is going to be a positive, which brings us back to what we have. So we didn't change it. We just kind of rewrote it in a different way so that it can mimic the form that we need to have it in. We need to have it x, and the form set up as x minus something. So we got that and enabled it. And so, and what that means, though, is that clearly states that h is equal to -1. So we can label all the points at this. So we say A is 9, H is -1, and then K is equal to 3. Right here. Here's the 3. So K is equal to 3. This is the vertical asymptote, so it's the one that goes up and down. If we've got a coordinate plane, it's the one that goes up and down, so it's going to be right here, and that's the line x equals -1. And this is horizontal, and it's going to be right here. So 1, 2, 3, and that can be represented by the line y equals 3. Vertical and horizontal asymptotes. Okay, so now we just need to fill in the table, in the chart, and that's pretty straightforward. So we're just going to go h of -10, and we're just going to crunch numbers, equals 9 divided by -10 plus 1 plus 3. Wherever we see an x, replace it with -10. So we're going to have 9 divided by -9 plus 3, and that's going to be -1 plus 3. That's going to equal 2. So when x is -10, h of x is +2. Let's take a look at, we'll just take a look at a couple more. Well, actually, I want to take a look at this one here. Let's take a look at h of -1 is equal to 9 over -1, put it in parentheses, it really helps, plus 1 plus 3 is equal to 9 over 0 plus 3. Oh my gosh, what do we have here? What do we have here? We have something divided by 0 that is undefined. Undefined. And if something is undefined, you can't define it by adding 3. Adding 3 isn't going to help you. Multiplying by 3 is not going to help you. Dividing by 3, subtracting 3, nothing is going to help you. Once it's undefined, game over. Game off. It's done. It's undefined. Undefined trumps everything. You can't bring it back to life once it's undefined. There we go. And plus, look at that. Don't we recognize that? That's the vertical asymptote, -1, when x equals -1. Okay, so let's maybe try, well, yeah, we're kind of running out of time here. You get the gist. You know how to do this. You replace x for whatever values are here, and then you plop them in right down there. So let's take a look. I've got the table filled in. So here we have our original function, right? A rational function. We've identified the vertical asymptote. We've identified the horizontal asymptote. We've completed the table of values. So now we have all the pieces of information that and remember, so these are the values of x and h of x. Another way we can do that is represent that by y. So we've identified a bunch of values for x and y. So we can rewrite that as what? -10, 2. So we can put it in an ordered pair like we used to sing. -7, 1.5, so on and so forth. So now we've identified a whole bunch of points, and we can go off to the races and we can graph this. Let's take a look at what the graph looks like. Here it is right here. Here's the graph. So what we have here is the vertical asymptote of x equals -1. The horizontal asymptote of y equals 3. And we have a bunch of points. Here are some of the points. When x equals -10, y equals 2. Right here. When x equals -7, y equals 1.5. Here it is here. When x equals 0, let's see. When x equals 0, y equals 12. Oh, I'm losing it. When x equals 0, y equals 12. Right here. When x equals 2, y equals 6. 2, 6, 0, 12, and so on and so forth. So I hope you found this helpful.